Well, hello, everybody. Good evening and welcome to In the Cosmos Live Deep Sky Edition. As always, I am Toshi Komatsu and I'm the director of the planetarium at De Anza College. And with me, as always, is my good friend and my partner in crime here, Mike Askins. Why don't you go ahead and say hi, Mike?
Hi, everybody. I'm very happy to be with you tonight. I'm missing being at the planetarium, as many of you probably are as well. I know that we've got planetarium patrons. We've also got um, people in other cities as well. Some have good weather, some have bad weather. Anyway, I'm just very pleased to be here. I hope you enjoy the show tonight. And back to you, Toshi.
All right, thanks, Mike. And also this evening, we have a special guest with us as an old friend of ours and actually a former boss to both of us at different points in our careers. But we have with us Alan Gould, who's the director emeritus of the planetarium at the Lawrence Hall of Science at the University of California, Berkeley. Alan, if you could go ahead and say a few words, say hello and say a few words.
Well, hello, greetings from Berkeley, California. I'm right here in Berkeley, although it is cloudy out tonight. So we are we had some nice clear nights recently, though, so that's good.
All right. Well, we're very happy to have you with us, Alan, even if the weather isn't quite so cooperative as we would have hoped. But before we move on, we do want to acknowledge, as always, the Foothill De Anza Foundation for their support of our star parties. And we also want to acknowledge, of course, that the weather is not what we would have hoped for this evening. Unfortunately, it's quite cloudy locally here in the Bay Area. And we're expecting some rain in a few hours, depending on where you are in the Bay Area here. But however, on the flip side, if this were an in-person star party, we would have just canceled the whole thing due to weather. But one of the few benefits of having a virtual program is that we can still present something to you live. So we were going to be showing some views through telescope, live telescope viewing, as we have been doing in the past. But unfortunately, we aren't able to do that this evening. So we're hoping for clear weather next time at our star party, which will be on Saturday, May 15th, which will be Astronomy Day 2021. So we're hoping for some clear weather on that date. And again, we'll hope you'll join us for that. But in the meantime, we'll be showing you some images that we took earlier in this week and some previous images so that we can take a look and see what sort of things we might have wanted to show you, even though the weather is not clear tonight. So we hope you stick around for that and can join us again on May 15th at 9 p.m. But what we're going to do is we're going to go ahead and for now, take a look at our old friend Stellarium to just get a sort of a handle on the sky and what sort of things we would have been looking at if the weather were clear. So we'll switch over to Stellarium here. This is the view that we would see if it were clear. Unfortunately, it's not. It's a real-time view. So we're looking at tonight, April 24th at 8:33 here in Cupertino. And we're looking towards the western part of the sky. Again, if it were clear, we can see a famous constellation right over here with 3 stars all in a row. That makes up the belt of this famous constellation that we can see in the sky. The dot-to-dot version looks a little something like this, and probably a lot of our viewers here recognize this as the constellation of Orion, the Hunter, and he looks a little something like this here. He's there fighting someone in the sky. It's a little bit too bright still to see all the stars of this constellation here. But if you take the belt stars and you go along this way, right along towards the right, there's a bright star there. That's a star that is the brightest star in the constellation of Taurus, the Bull there. And as you'll note, both of these constellations are quite low in the sky here as the sun is setting. So they're really just about to disappear for the season, but we did want to point those out. Once the weather does clear up, hopefully in the next couple of days, again, locally here, you might want to take a look in the west right after sunset, get your last look at these winter constellations.
And Toshi, I know that if people wanted to see those, they would have to have a very flat horizon, correct?
They would have to have a pretty flat horizon here because, again, they're quite low there in the sky. But if you were to look a little bit higher above the horns of Taurus the Bull at the moment, there's a red spot there in the sky, and that red spot is actually a planet, and that's Mars. So Mars is right above the horns, and it'll be above the horns for another few weeks, several weeks, that you can see it again if you look right after sunset. But we've had some exciting news from Mars, especially this week. A couple of big milestones that have happened. NASA's Ingenuity helicopter made its first successful test flight. Actually, it made 2 successful test flights on Mars. And so we have powered flight on another planet. So that's definitely a first. And for the first time, one of the instruments on the NASA Perseverance rover was able to make oxygen from the Martian atmosphere. So both of these are incredible milestones paving the way for future exploration of Mars.
So Toshi, I was just as I was looking at those 2 movies again of the of Ingenuity there, it said that tomorrow there was going to be a 3rd flight. Did you hear that?
I did hear that, and I was going to say that there are additional flights that they are planning for Ingenuity that are coming up still. So there's still more news to come from Mars, especially in the next few weeks. And certainly Perseverance is doing a lot of great work there as well. So, but back to Stellarium and looking at the constellations here again, we're saying goodbye to the winter constellations. What I'd like to do now is to go ahead and pan more towards the east. I'll pause over the south, where if we look high up in the south at the moment, there's a famous constellation that we can find with a bright star. Let me get in a little bit closer here, see if I can get that star name to show up there. There's Regulus. Oh, not sure why it disappeared there, but Regulus is the brightest star in a constellation here that has several other bright stars that make sort of a backwards question mark shape there, hook shape there. This is a constellation that is Leo the Lion, and that's a sure sign of spring when you see Leo in the sky. And then backing away from Leo a bit and moving downwards, again, moving towards the east, there's another star sort of right below where the moon is tonight, looking towards the southeast. There's a bright star there. That star is called Spica. See if I can get the name to show up. There we go. There's Spica. And that is tricky. Stellarium is being a little bit tricky tonight here. But that is the brightest star in the constellation of Virgo, the maiden here. And I'll back away so that we can see Virgo and Leo together there in the sky. And those are certainly springtime constellations. And when we see them, we know that we're in the midst of spring. And the other thing that you might note as I come back a little bit here, you'll notice that the moon here tonight is right in Virgo. And normally, if you've been to our previous star parties, you know that we spend a lot of time looking at the moon. And usually we're doing that with Mike's telescope. And unfortunately, we've been kind of limited to looking at bright things with Mike's telescope because he's using his phone to take a look through his telescope, looking at something bright like the moon, and then broadcasting that over to YouTube. So we're limited to bright things. But as you probably are aware, there are other things in the sky besides just the stars and just the moon. Stellarium can show us where several of these different objects are. Here I brought up some of the deep sky objects, or DSOs, if you want to sound like an amateur astronomer. DSOs, deep sky objects, where we can see several things like these red ovals there. Those are galaxies. Each one of them is a galaxy, and you can see that there are several of them right in between where Leo and Virgo are tonight. They happen to be near the moon there. As we move over in our view here a little bit, some other things that we can see. There's a couple of clusters that I'm panning back over here. Those are circles with dotted circles there, and we'll be able to see an example of a cluster tonight. And then there's also some other things. There's some green squares that you can see here in the view as well. And those are nebulae, big clouds of gas out in space here. And so several different things, but these things tend to be quite faint in the sky, which is why we would need a different kind of telescope, not just Mike's. Mike's telescope is a great telescope, but it's one that isn't so conducive for looking at these fainter objects and broadcasting it over the internets out to all of you fine people here.
Well, Toshi, I hope that we will be able to see Casper the Friendly Ghost Nebula. I'm looking forward to that.
Maybe one day, Mike here. But so as I said, normally we'd only have access to Mike's telescope, but the reason why we brought Alan on is because he has a different kind of telescope that would allow us to view some of these fainter objects. So I'm going to turn it over to Alan for a moment here, and so he can tell us a little bit about his scope and why he wanted to get one.
Well, thanks, Toshi. I've been observing for many, many years, actually, and I've had various size telescopes. You usually tell the amount of light gathering power, or how powerful the telescope can be in terms of how it can make dim things bright, by the diameter of the telescope. And so I made a 6-inch telescope when I was young, and then I had an 8-inch telescope, and I bought a 10-inch telescope to view things in the night sky. But the bigger the telescope you get, the harder it is to lug around. So one of the reasons why I bought this telescope, and I have it here. This is a, let me hold it up for you. It's called an Evscope. It is it's only about 4 or 5 inches in diameter. And so it's a relatively small telescope, and you can tell that I can hold it up very easily, and it has a really nice solid tripod. So the reason why I bought it partly is because it's such a nice lightweight telescope and I carry it around easily. But the other part is that I've been afraid of doing astrophotography most of my life, because it's a hard thing to do, to get a camera connected to a telescope to get decent images. And this is the astrophotography for the complete idiot. It's so easy to take a photo, an astronomical image with this telescope. Even I could do it with my fear of astrophotography. So that's the other reason. Actually, there is yet one other reason, is that it has a very good automatic finding system. It can find objects in the sky by a computer control. And that's another thing that I really like about it.
Well, Alan, you're sort of maybe cutting yourself a little short, because you know a lot about the sky, but it can be difficult to find things. Even people who know a lot about pointing telescopes can sometimes have trouble. And it's very nice to have a system that sort of finds out where it's pointing and corrects and points to exactly where you want it. I can understand that.
Yeah, they call it a go-to system.
Go-to, yeah.
Well, thanks for sharing that bit with us, Alan. And again, unfortunately, we aren't able to look through the Evscope. That was our hope for tonight. But instead, what we do have are some images that we took a little bit earlier. And so we'd like to take a look at those images. We'll take a look a little bit about the interface that the Evscope has, which is controlled by your phone. Actually, that's a nice thing, is that you don't necessarily have to look through the eyepiece. Even though your Evscope does have an eyepiece, you don't have to look through it. You can actually control it with your phone with an app. And so we took some images, the three of us, Mike, Alan, myself. We met a little bit earlier this week when the weather was good to get some images. So what I'd like to do here is to go ahead and share our slide deck that we put together that has some of these images. We'll look both at the images that we took with Alan's Evscope, as well as in comparison, some Hubble images, what are normally what people think of when they think of astrophotography. And again, there's a lot of people, we all have friends who do astrophotography, and it does, as Alan said, take a lot of work to get anything that's sort of resembling Hubble. You can do it, but it does take a lot of work, and the Evscope makes things really simple here. So let's go ahead, take a look at, again, you can kind of see this is the Evscope. This is what Alan was holding. Again, nice solid tripod, not very big at all, easy to lug around, as Alan said. That's always helpful. But also another thing is that you don't necessarily have to go out to a dark sky site. You can do a lot of observing right in urban landscapes as well, where there's a lot of what we would say light pollution, even with the moon. That was the other thing, is that the moon is almost full this evening. And looking at the moon with Mike's telescope would have been very, very bright. So we're able to skip through that. And the Evscope is able to show us much fainter things here. And so just to give you an idea of how it works, the light comes in and it bounces, and then everything's read off of this sensor. Even the eyepiece that's on the Evscope, it's actually just reading what's directly on the sensor. So when you're looking through the eyepiece, you're not actually looking directly at the object. You're looking at whatever the sensor is picking up, and there's an onboard computer here. But enough about the telescope. We're not trying to sell the Evscope. We're not sponsored by Unistellar, which makes the Evscope here. But let's go ahead and take a look at some of the images that we captured earlier on. So this slide here, there's 3 images here, and they give you an idea of what the interface of the app looks like here. Once you get a lock, as Alan said, once you get a lock on the sky and the scope knows where it is, then you can sort of type it in. Like if you've seen me do Stellarium, you can type in object names in there and it'll go, Stellarium will tell you right where it is. Well, you can type it into the Evscope and it'll slew or move towards that object. And so here we're looking for the Great Nebula in Orion, which we saw just a few minutes ago in Stellarium here. And then eventually it locks on to the object. And then there's this funny button down here that activates what it calls the enhanced vision. And this image shows after 20 seconds, you can already see that there's a little bit more detail that you can see compared to just sort of the what you might get through a telescope like Mike's, just looking with your eye.
So Toshi?
Yeah.
Let me just mention to folks, so the name of this first object that we're looking at, it's called the Great Nebula in Orion, but it has a very interesting sort of sub-name that amateur astronomers call it all the time, which is M42. M stands for the Messier catalog, and there are 110 objects made up by the French astronomer Charles Messier in the late 1700s. He was looking for comets, and he started writing down fuzzy objects that weren't comets so that his friends wouldn't turn in results of finding comets, and they turned out to be something that wasn't a comet at all. So he made a lot of notes about objects that were in the sky, and this is number 42. You'll find that we'll refer to some of these objects by their Messier number, but I just thought I would throw that out there to make sure that you understand it if we start talking about it using the numbers.
Yeah, and for many amateur astronomers, the Messier catalog, it's a good catalog of objects that cover nebulae and star clusters and galaxies, good targets to look out for, even though it's sort of a list of all of Messier's mistakes. It's 110 mistakes, things that were, again, not comets. So it's a catalog of mistakes, but it's a good one that we use even today, several hundred years after Messier.
I see a couple of messages in the chat there, Toshi. One of them says, where do you get them from? I'm not sure exactly what that question was, and can you download them? So I think they're asking whether or not they can download these particular images. And we don't have those. We actually, these are Alan's pictures. Do you have a response for that, Toshi?
Well, so that when using the Evscope, you can download them onto your phone. Or maybe Alan, you can correct me. I think it gets downloaded onto the computer. You can access them via your phone there through the Evscope itself. But these are all going to be images, except for the Hubble images, and you'll be able to tell. Sorry, Alan, but you'll be able to tell which are the Hubble images and which ones Alan took with his Evscope there. But these are all ones that that Alan took with his Evscope over the course of a few nights when we were looking together.
If you want to make them available, it's okay with me. They're
okay. Well, we might post a few to our social media or something like that later on. So do check out our social media, and you can get some examples that we're sharing here in the slide deck.
So so maybe we could talk a little bit, Toshi, about the difference between the images, the left one, the middle one, and the right one. The way that this telescope works, unless Alan, maybe you'd like to talk about this, I can go ahead. Basically, there's a longer amount of time going from the left to the right, longer amount of time from image to image that the image has been collecting light. So we started out with just some very quick images, and over time, it keeps adding more and more images to the accumulated group. It sort of grows them over time. And by over on the right there, you see that 20 seconds had gone by that image had been accumulating for. And as we continue to watch, that will continue to change.
Yeah, so here are a couple more images, just focusing on the images that you get from the Evscope here. Now, this image here on the left, this one was after about a minute here, 56 seconds here. So again, you can see a little bit more detail here. And this was an image that was exposed for about 2 minutes. So you can see that the longer you leave, and that's kind of the magic, I think you'll agree, Alan, that this is the magic of the Evscope, is the longer you keep the scope on the object, the better and better the image gets.
It's really astounding, actually, to see something like this growing before your very eyes. That's something that you don't see in other types of telescopes, and the colors are absolutely amazing to see. I have never seen colors in any of the previous telescopes that I saw. That, you know, the small telescopes that I had, and the small telescopes are bigger than this one. So this picks up color.
Yeah,
Well,
and I think Mike, maybe you can talk a little bit about your own telescope. What would it look like if we were looking through your own telescope at
it would be
this
very
particular
difficult.
object?
It would be very difficult, Toshi, to distinguish colors. This is a very bright object and not characteristic of lots of other ones that are up there in the sky. So it's maybe a special case because it's so bright. But it's sort of like a pale, to me, a pale greenish color, something like that, depending on exactly where you look. But the secret is 2 minutes worth of exposure. Your eyes can't collect that much. They collect, just a tiny bit of light constantly. And you're seeing it live. That's an advantage, but you're not seeing an accumulation of the light as it comes in. And that's really the secret. And also the reason why it works so well in an urban environment. Maybe I could ask you to speak to that, Alan. Just the fact
An urban environment. Well, especially on a night like tonight when the moon is approaching full moon pretty soon. Even a bright object like this is it's not that hard to find when it's this bright, but the really faint objects are just hard to find. And once you've hunted it down, you start to wonder, well, is that really the object? Because it's so faint and it's so blurry and this, to have an image built up like this by the process which we call stacking. It's like taking a whole bunch of pictures and stacking them all together. It makes it much, much brighter and much, much more contrast.
Yeah, and it's a process that amateurs and professionals use to show greater and greater detail in an image when we're looking at an object. So again, if you just were to take a quick snapshot, again, we could probably, or Mike could probably see this through his telescope if he looked with his eye. But for us to show you this over YouTube, to stream the view from Mike's telescope, probably would be very difficult. Again, it's bright, but you might see a fuzzy thing, but we wouldn't see it nearly in this sort of detail, again, with the color, and we've got that bright center, and then you can really tell that there are all this structure in the clouds, even some of the dark lanes that you see here. And that's, I know that's what's always amazed me about any images that I've seen through an Evscope like this.
Well, this is amazing. It's the birthplace of stars. You might want to.
Yeah, I was going to talk just a little bit about that. This is a sort of a stellar birthplace, and there are 4 stars in the very center. That it's so accumulated. There's so much light there, but you can't actually see the 4 bright little stars there called the trapezium, which Galileo discovered when he first started looking at the sky with his telescope. And we'll see those in just a minute. We're going to compare the image here to what what the Hubble Space Telescope sees. And maybe we can go ahead and do that. And this is not just a raw image from the Hubble Space Telescope. It's several images combined. But this gas cloud is slowly condensing. And as it condenses enough so far. You can see, maybe Toshi, you can help me point out the 4 little stars that are right at the heart of the gas cloud there.
Yeah,
those are the 4 stars.
Tiny little cluster of them right in the center there.
Yeah, the trapezium is what the name is. And my understanding is that the feeling is, or the understanding is, that whole nebula is mostly lit up by the ultraviolet light that's coming from those very, very hot stars. They're 15 to 30 times the mass of our sun, each of those. And they are producing a great deal of ultraviolet light, which is causing a lot of this interstellar medium, this gas and so forth, to fluoresce, kind of like minerals fluoresce with an ultraviolet light that you see in science class sometimes, or in a geology class, something like that. Ultraviolet light can cause things to glow, and it's causing a lot of this nebula to glow.
Yeah, and what I hope people can imagine too is, again, in the Evscope images that we were just showing, the ones Alan took, that this whole part was sort of overexposed, so it's very, very bright. But again, the colors that we're seeing here with the sort of the purples and the blues and these dark lanes here, those are things that we could see with the Evscope that I don't think I've ever seen in a conventional telescope. Just peering through, looking with my eye, you really need to again stack the image and or to build up the image to see this sort of detail here.
Okay, Toshio, I think we need to move on to the next object here, and maybe Alan, you can help us when we get to take a view of it. This is M67, as I recall.
Yeah, so this is M67, and it's an open cluster of stars here. And
so a cluster of stars is usually a group that formed sort of all at the same time. And those four stars, the trapezium that we saw at the center of the nebula that we were just looking at, that could be said to be a cluster. This is another one that's in the constellation, in the direction of the constellation of Cancer the Crab. And Alan, can you just make a comment about the likeness of the background in the image on the left versus the one on the right?
Yeah, well, when the telescope first finds the image, it's what we call a live view, and it's all it is a fairly short exposure, but any background light is showing through along with the stars. Mm-hmm. Now, when the process of stacking starts up, that background light starts to drop away, and only the objects that are of interest remain. So the background becomes very dark, and you can really see the cluster very clearly.
Wow.
And then comparing these two images, again, this one is listed here as 210 milliseconds. So as Alan said, very, very short exposure, it just kind of lets you know you've got the thing in your field of view here. This image here is just after 8 seconds. And again, you can see how much darker the background looks like. Part of the stacking process is to sort of make the things that you're interested in bring in more detail, but also figure out what's the background that maybe is not so interesting to look at. So that's why the background tends to get darker, so that the thing that you're interested in gets a little bit, there's more detail that you can see, and that tends to be brighter. And the stacking process is there to sort of bring out that detail.
Can actually, it looks to me like some of those stars actually have some colors associated with them. I see some blue stars, and I see one that's sort of yellowish. And just to mention to people that that the color of a star is directly related to the surface temperature of the star. So you can actually tell which ones are hot and which ones are cool by looking at the colors that you see. And we don't see a lot there, but I'm sure, Alan, if you were, we didn't get, this was difficult for us to get. This was on a night where there was a bit of wind there. It was difficult for us to get a really deep image. But I imagine you would see much more color if we could have looked at for a couple minutes worth of exposure for this object.
Yeah, that's another case where the colors are astounding to me. Those, of course, those in the know that it's actually the blue stars that are the hottest stars, contrary to what you might intuitively think.
Yeah. So I just wanted to also mention that this particular object is about twice as far away as the last one that we looked at. And as we talk about these objects, they sort of get further and further out into space. And this particular one is 2,800 light years away. What does that mean? That means that it takes 2,800 years for a beam of light or a single photon to go from the object to the Earth. 2,800 years. So when you look at these objects, you're really looking at them back in time. And we'll see some incredibly large numbers when we get to galaxies a little bit down the road here. But we also do have another image of this object that has a little more exposure time. And this one doesn't happen to be the, this isn't actually, this isn't one taken by the Hubble. This is the only one that's on, or one of the few on the website, the Hubble Messier catalog website, which you can go on and see all of these objects. This was taken by something other than the Hubble. I'm not sure exactly why that was. It was omitted from the Hubble site. Anyway, this is called the King Cobra Open Cluster. And you're going to ask me, why on earth is it called the King Cobra? And I looked online for quite a while until I realized that this is sort of a recent moniker that's been applied to this object. The guy who wrote the book where this appears, the name appears, thought he saw coils of a snake in the middle of the cluster there, and then that the head of the snake sort of reared up behind it. And I don't have a picture of that for you, but if you were wondering why it was called the King Cobra cluster, that's why. Some labels for things in the sky go back thousands and thousands of years. This goes back more like 10 or 15 years. So it's much more modern.
And I should also note that an open cluster like this, any open cluster, is generally a collection of maybe a few hundred stars. They tend to be quite young. It's what something like the Orion Nebula that we're just looking at, M42, that it will turn into something that probably looks like an open cluster when all that gas comes together and it's formed all the stars it's going to form out of all the gas that's available to it, that it'll probably form an open cluster. So what we're seeing are stars here a little bit older than the stars in the trapezium in the Orion Nebula there. So we're also seeing stars at different stages of their own lifetimes.
And we've looked at this open cluster now. We're going to contrast that with the next object that we want to show you, which is something called a globular cluster, which instead of just a few stars, maybe 500 as in the last object that we were just looking at, this has more the size of like hundreds of thousands of stars. And Alan, it looks to me like we're seeing a lot of background sky in this first image. It looks like this is a less than a second worth of image.
Yeah, I think on this one, it doesn't, a lot of times it puts the name of the object, the Messier number in it, and it did not do that on this one, which meant that it was probably having a hard time finding it. And it happened to go by it, and I spotted it, and I said, hey, stop looking. We have the cluster here.
So maybe we can look at some more grown images here that have over the period of time have grown. Maybe Tush, you can show us the next slide there.
Yeah, again here, so we're seeing a lot of background light here, and we've sort of just got the image in the field of view. But once we start, again, stacking those images, Whoa. This image here on the left is 2 minutes, and this one on the right here is also 2 minutes. But then we started to, or Alan, I should say, on his scope, started to play with some of the other features that you can do with the Evscope as it's live. So Alan, maybe you could say a few words about how we were able to adjust it, or how you were able to adjust it to get a little bit more detail here on the right.
Well, there were automatic things that it uses, automatic settings. But if you remove the automatic settings, then there's two controls that you have power to change. And one is called exposure, where you're essentially controlling the brightness of it. It's like controlling the brightness of a picture if you're modifying a picture. And the other is controlling the background. So we can reduce the level of light in the background and make the background darker. So those two controls, by adjusting them carefully, can bring out more detail.
Yeah, and so in both of the images, a little bit more obvious on the right. That's why we kept this image. But there's sort of a globular cluster is sort of like a global distribution of stars. These tend to be older stars, but you tend to have more of them sort of at the center. And so that's why it's very bright. But there are, as we look sort of on the edges here, other stars that are sort of part of this cluster still. Again, in this case, several hundred thousand stars perhaps instead of just several hundred stars here, but they're all kind of grouped together, but it extends quite a bit of ways from that very, very bright central core there.
And let's see here, in my notes, I'm trying to see what's interesting about, light takes about 35,000 years to get to us from that object. So it's a little bit farther out than we were talking about before. The other interesting thing about globular star clusters is they tend to be extremely old stars formed at a very early time in the history of the universe. So it's really something to be able to look at these things. They're also not in the disk of the plane of the galaxy. They're sort of clustered around the center, the nucleus of the galaxy. And maybe at some point, when we talk more about galaxies, we may be able to show some galaxies, maybe in another program, and talk a little bit about how those globular clusters are sort of arrayed around galaxies.
I think we have some galaxies here.
Yeah,
we do. So shall we go ahead to the Hubble?
Yeah, let's go ahead and look at the Hubble image here. Again, you can kind of see, again, this is a lot of detail that you get with Hubble. One of the things that Hubble has the benefit of is it's a space telescope, which means that it doesn't have to worry about the atmosphere distorting the view that you get. And I often tell Mike that if we only could get rid of our atmosphere, then we would be able to take much better images and things would be a lot simpler. Mike, you always shoot that idea down, though. I don't know why.
I do, because I like to breathe, Toshi. Thanks.
Oh, well, would you rather breathe or have beautiful images that you could get
now you're making it hard. Oh, well. So about 150 light years across this object. So from one star at the very extreme edge to the other side, about 150 years it takes for a photon to go from one side to the other. We are talking about huge, very far away things, and only going to get more huge and far away, right, Toshi?
Yeah, and when we start looking at these faraway things, I know I have a friend who likes to say that he's collecting ancient photons, is the way he puts it. Because again, as you said, Mike, the further away we look, the older the light is, the older these objects are. So,
well, Toshi, I'm thinking time looks pretty good here. Maybe we could go on to one of the galaxies.
Yeah, and as we have a couple galaxies lined up here. And as we're showing these, again, if you have questions that you have, audience, you can go ahead and put that in the YouTube chat, and we'll be able to see some of or we'll highlight some of those questions. So do feel free to ask any questions that you have about either the Evscope or observing, or about any of these objects in particular as well. But here we're yeah, go ahead, Mike.
Sorry, Toshi. I was just going to say there was one that someone chatted that we didn't answer. About, does the universe expand forever or does it stop? And I guess there's a lot of discussion and research that goes on into questions like that, Toshi. Do you have an answer that you'd like to share?
Well, the short answer is that we do think that the universe is expanding and it is getting bigger and bigger and bigger. And about 20 years ago, a little bit more than 20 years ago, maybe 25 years ago now, there was a discovery for which later a Nobel Prize was awarded. That was the discovery that not only is the universe expanding, but the rate at which it's expanding is actually accelerating, that we're expanding faster and faster and faster. So as far as we can tell, it's going to go on forever and ever and ever, and get bigger and bigger and bigger, faster and faster and faster.
But I won't be around for that, Toshi.
Well, I don't think I will either.
Sometimes there's a little bit of subtlety to this. When you say the universe expands, a lot of times people will picture something that is a thing that's getting bigger.
Yeah.
And that's not actually what it is. The universe the universe probably is something that is infinitely big, or it may be infinitely big. But when we say it's expanding, it means that each part of it is getting farther and farther away from each other part of it. But the whole universe may well be infinite in extent.
Yeah, it does get complicated and at times very philosophical, maybe philosophical. There's a lot of metaphysics that get into it. A lot of it has to do with that. These are things that are outside of sort of normal human experience. And so in some ways, it's a bit of a failure of human language that we just don't have the words perhaps to explain what's happening on these very large universal scales, because it's just so outside of the human experience there.
Okay, well, why don't we go ahead and talk about this M64? It's called the Black Eye Galaxy, and I think it's pretty well named. But maybe either Toshi or Ellen, maybe you could talk about sort of the difference between those three images there. It looks like the first one was less of exposure and more exposure going to the right. Is that right?
Yeah, so we're building up the exposure time here. This first image is a 12-second image, and you can kind of see there's a fuzzy thing there. This next image is after 60 seconds, so this is after a full minute, but you can start to see a little bit of structure to it, that there's a bright thing, and then there's a dark thing sort of to the left of the bright nucleus there. This last image that we're showing here, this is after 8 minutes. And so not only can you see the nucleus of the galaxy and that darker part there, but there's also, you can start to see sort of where the spiral structure would be. So sort of an oval shape surrounding the galaxy around there. So again, we're building up this image a little bit at a time. Again, if we had live access to the Evscope, we'd be able to watch it building up in real time. We just took some snapshots to share with all of you here because of the weather. But Alan, did I miss anything? Anything you wanted to add before we look at the final image that we got here?
No, it's just again, it's neat to watch the stacking process go as it gets more and more detailed that you're seeing.
And also, if you look carefully, audience, as well, you may notice that even some of these background stars, you're just starting to see a little bit more detail, because again, part of the stacking process is to kind of try to eliminate the bright background and just leave sort of the bright stars. So the final image that we took, this was after 7 minutes here, but again, I think we played with the brightness and the exposure a little bit here. But hopefully you can see, audience, why it's called a Black Eye Galaxy here, that there's that sort of very dark lane there. And you can I can almost convince myself that I'm starting to see a little bit of spiral structure here as well. But certainly that dark lane there, that's where it gets the name Black Eye Galaxy.
That dark lane really looks like a black eye to me. And it's very interesting. This is not something that's found in other galaxies, or at least not to this degree. What astronomers think has happened by looking very carefully at the rotational directions within this galaxy, there's two different parts of it. Part of it is rotating counterclockwise, and part of it is rotating clockwise. That does not happen in typical spiral galaxies. And what astronomers think maybe has happened there is that a very long time ago, possibly 1 billion years ago, the theory is that there was a companion galaxy, a satellite galaxy of this one, that collided with that M64 galaxy. And that is the reason why we're seeing some material behaving one way and other material behaving a different way. And I thought that was very interesting. And it'd be very interesting to know what current research. I did some checking. This was on the Hubble site, the Hubble Messier catalog site. They described this process that they think is going on in there, but very interesting. I want to check my my notes here. I know that this is something on the order. This galaxy, okay, is 17 million light years from Earth. 17 million, not 1,000, but million light years. So this is 17 million year old light, to harken back to what Alan said, his friend, or maybe it was Toshi, who said that they talked about harvesting ancient light, because that's what we really did with Alan's telescope with this object.
Mike,
Right, yeah.
it's interesting how the series of objects is, I just noticed that the first objects we were seeing were just a few thousand stars or a few hundred stars.
Yeah.
And then the globular cluster was maybe 100,000 stars.
Hundreds of thousands, yeah.
So can you tell us, so we're getting things that are farther and farther away, bigger and bigger objects, but more and more stars. So do you have that number?
I don't.
We don't know how many stars are in this, but what is the order of magnitude of a number of stars?
Well, the order of magnitude is something like 100, like hundreds of billions of stars. So the Milky Way is something like 100 to 200, 300,000 to 300 billion stars. And similarly with a galaxy like this, and like I say, I have to look up this particular distance because I don't actually have that in my notes. But it's on that order, hundreds of billions of stars.
Yeah, that usually blows my mind, because this just looks like this fuzzy thing, it just looks like a cloud, but it's actually made of that many stars.
Yeah, it's quite amazing.
Yeah, truly is amazing to think that, again, all that in this, when you think of a spiral, in fact, let's go ahead and look at the Hubble image there. You can start to see some of the individual stars in this galaxy here. But in the spiral arms, that's all stars there. And this fuzziness that you can see in this image, even in this image, there's some fuzziness, that is all made up of stars, those hundreds of billions of stars that you were just talking about, Mike, there. And so it's galaxies really, in many ways, they're collections of hundreds of billions of stars, and they might be tens or even hundreds of millions of light years away from us. So
kind of running a little short on time here, Toshi. If anybody's interested in looking at the Hubble Messier catalog for M64, you can see the description of this image and exactly how it was made. It was kind of interesting. We've got one more galaxy to show, and it's one of my favorite galaxies, I must confess. So, Alan, can you maybe say a little bit about the differences there between the images and maybe some of the duration, stuff like that?
Well, I can start with the duration,
Okay.
just because it may be a little bit difficult for people to read here. But this is sort of when we first locked on to the image of this galaxy, and there's actually a couple of bright things that you can just see, but they're just very faint and somewhat fuzzy. There's a lot of background here. This was 500 milliseconds. This is a 68-second exposure. And here you can see what you can probably convince yourself, audience, here as a galaxy. And then another bright thing, this last image that we're showing on this slide is a 5-minute exposure. So again, definitely a bright center, characteristic of spiral galaxies, and some definite spiral structure to this galaxy. There's even a little companion galaxy, again, bright nucleus there with some fuzziness surrounding it there.
I might add that with a telescope that does not have this built-in stacking feature of adding images together, you might not be able to see that spiral structure very well, if at all.
Yeah,
no,
you might see the bright spots, the bright nucleus. You might, depending on how large your telescope is, typically like the Evscope is about 4.5-inch mirror, I believe is what it has, about 4.5 inches. But to get sort of the detail that we're seeing here through just looking through a telescope, you'd probably need a telescope that's, I don't know, 12 inches, 14 inches, maybe even larger, to see even this sort of level of detail here with some of that, to make out that the fuzziness surrounding the bright spot is that has some spiral structure to it.
Well, maybe we can see the final image that Alan was able to get. It really is.
This is after 8 minutes, and again stacking this image here to get the level of detail that we're seeing. And I think, Alan, we probably adjusted the brightness and contrast a little bit on this one as well. But again, very, very distinct nucleus there, and very, very distinct spiral structure to it, with some fuzziness around the spiral as well. And there's definitely some kind of interaction with these two galaxies together. The main galaxy here, this is, by the way, called the Whirlpool Galaxy. It's probably pretty obvious why it's called that. Definitely looks like a whirlpool that you might see in the sky, and sort of your classic spiral galaxy that we're looking at here.
This is 23 million light years from us, Toshi. The estimated diameter of the main one, is about 76,000 light years.
Right.
Wow.
So 76,000 light years. That means it's a little bit smaller than our own Milky Way galaxy.
Yeah.
Then.
Yeah, just a bit.
Coincidentally, that actually is about the same. I think it was 23 million light years to the Black Eye galaxy. I just looked it up.
Oh, okay. Yeah, just a little bit less.
Yeah.
And with the yeah. So it's
so
pretty
what
amazing
about
detail
the Hubble image there, Toshi? Maybe we'll finish up with that. Whoa.
Yeah.
Now this is
and
actually taken in several different wavelengths. So you have to be careful with astronomical images, because a lot of times astronomers will bring out features by using color. And so it's sometimes called false color in that sense. But there are a lot of false color little bits and pieces that you're seeing there. Again, if you go on the Hubble Messier catalog site there and look up the description for M51, you can see some of the details about that as well.
But again, similar to, obviously there's a lot more detail in this Hubble image, but like we saw in the Evscope images that Alan took, again, bright nucleus for the smaller galaxy with some surrounding fuzziness around it. And again, that bright nucleus with the spiral structure, again, bright in the middle of these spiral arms there, but some fuzziness surrounding that spiral structure as well. And it's within these spiral arms that you have new stars that are forming, and that's true in our own galaxy as well.
Well, Toshi, maybe we ought to take a look at the chat to see some questions that, let me go back just a little bit here.
Well, I did note someone was asking about how we know the universe is expanding. We touched upon that a little bit earlier. So how do we know that? Is there data? Some of the data that astronomers look at to verify that the universe is expanding is way back when with Edwin Hubble, almost 100 years ago now. What he noticed were these very special stars in a galaxy. It was actually in the Andromeda galaxy, but he noticed a very special kind of star that was a pulsating star. And there was a characteristic of that pulsating star. If you could measure how fast it was pulsing, I don't want to go into all the physics details at the moment here, but if you could figure out how fast it was pulsing, you could figure out how far that star actually was by comparing its apparent brightness with how bright it should be based on how it's pulsing. And so he found, first of all, that there was a whole other galaxy out there that's what separated, or that's what sort of opened up the universe to let us know that the universe was much larger, because it used to be called the Andromeda Nebula. Then it became the Andromeda Galaxy once we determined it was galaxies. But once we're able to look in other galaxies. What we can also see sometimes are supernova. And some of you may have heard of supernova before. That's when you have gigantic stars that explode. Nova actually means star because they look like a super bright star. And those also shine with a characteristic pattern that if you're a supernova astronomer, you can study them. And based on how these supernova look in the sky, you can tell how far away they are. And that gives us an idea of the expansion of the universe. Again, I'm skipping a lot of steps there, but it's by looking at supernovae in distant galaxies that we can figure out that the universe is expanding. And also, we just look at these galaxies, and as Alan alluded to before, we just look at them. Once we had telescopes that were good enough to observe these galaxies, we saw them all moving away from us. And it's not like, this is a joke I take from one of my astronomy professors, that it's not like we have cosmic cooties where all the galaxies are running away from us, but that's what it appears like. All the galaxies, they're all moving away from us in a way that only makes sense if the entire universe is thought to be expanding, as we mentioned earlier there.
Except for one of the closer galaxies, which is coming towards us.
Ah, yes, yes.
There's a question that's in the chat that I'd like to address here, although we've only got a couple minutes left. How come we use telescopes to take a picture of a black hole, but can't use the same telescope to take pictures of exoplanets? What an excellent question. It's all a question of scale. The pictures of black holes at the center of galaxies are humongous. Unfortunately, exoplanets are way, 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 way smaller. The problem with finding exoplanets is that they are circling stars that are far away, but they're also very, very small. Toshi, would you like to elaborate on that at all?
Yeah, I'll just add that exoplanets, they're also not giving off their own light. So they're reflecting light from their parent star. So again, there's very little light for us to collect, as opposed to, again, when we're looking at something like a galaxy, we're looking at the combined light of hundreds of billions of stars all at once. Now, in the case of a black hole, if you're referring to the image of the black hole that was taken last or released last April, so it's been just about a year now, that was taken through a sophisticated network of several telescopes working around the world to put that image together. And there was a lot of sort of very high level physics to make that image happen. But again, a black hole in scale is going to be much larger. The black hole that they imaged has the mass of, well, the black hole that's at the center of our galaxy has the mass of something like 10 million suns. The black hole that they image is even bigger than that. So again, there's a lot of energy to be working with that faraway black hole, as opposed to, as Mike said, with the exoplanet, which just has just a little bit of light. So we have a lot of good exoplanet data, but not so much the imaging of the exoplanets themselves there.
So real quick, what are the red objects on the spiral of the Whirlpool Galaxy? Again, if you do a web search for Hubble Messier catalog, you'll go to the website that describes these images. But basically, that the red stuff is infrared light and hydrogen gas clouds. Quick question, because we're really out of time, right, Toshi?
Yep, and I think we're probably want to sort of wrap up with that. The last thing that we do want to remind everybody again, first of all, we'd like to thank everybody for coming this evening. We hope you enjoyed yourselves. We hope you learned a little something. We certainly appreciate all of your questions. And we'd like to, again, extend our thanks to the Foothill De Anza Foundation for their support of these virtual star parties. But we do want to mention one last time that, again, we're going to be trying this again, hopefully with live telescope viewing through the Evscope. So you can see it live and in person here on Saturday, May 15th. So that's just in about 3 weeks, starting a little bit later at 9 p.m. because it won't get dark until about 9 p.m. So hopefully you'll be able to join us for that in just about 3 weeks from now.
And we'll cross our fingers. Sorry, Toshi, we'll cross our fingers that the weather will be better so that we can actually have Alan do the telescope right in front of us.
Yeah. So hopefully everybody hope for clear weather so that we'll be able to use the telescope here. But in our remaining couple of minutes here, again, I just want to extend our thanks to Alan Gould, who was able to join us again, unfortunately not live with this telescope, but we're always happy to see you live and in person yourself, Alan. I know Mike and I learned a whole lot from working under you, so we appreciate your time here. And also thanks to my cohort here, Mike Askins, who helps us in the planetarium when we're in person. So many thanks to both of you this evening. And any last words from either of you before we finish off?
No, just thank everybody for coming. And we got to get the county and the COVID to cooperate so we can get back in the planetarium again.
I want to expound for about 20 more minutes about the expanding universe.
Well, why don't you do that? But we're going to have to flip the switch, though. Sorry, Alan.
Well, we'll see if we can cover that on May 15th. So we'll leave something for folks to come back to in 3 weeks. So, but I think with that, again, thank you very much, Alan. Thank you, Mike, as always. And once again, thanks to all of you for coming to watch our virtual star party here. We hope to see you at the next one. And again, everybody hope for clear weather so that we can look through the Evscope. But have a great rest of your evening. And if you are watching this later on YouTube, thanks for checking us out. Do check out, again, all of our social media. We'll put those links in the YouTube description below. But thanks very much, everyone, tonight, and have a great rest of your evening. So signing off here from the De Anza College Planetarium.